I'm going to go ahead and get started. Today we're going to be looking at section 5.1 from your book. That's mostly what we're talking about in the module this week. And we're looking at number theory and prime and composite numbers. And we're going to start by thinking about different types of numbers that we know about. And so you probably remember back when you were learning to count, or if you have a small child that you're around, you probably, are maybe helping them learn to count. And we start with what we call the natural numbers. We also sometimes call them the counting numbers. 1, 2, 3, 4, 5, and on it goes. And then we build on number systems from there. So when we're talking about prime numbers and divisibility, we are talking about these natural numbers, or what we call the counting numbers. And one of the other important things to know about is factors. And factors are just numbers that we multiply together to create a product. So in this first example at the bottom here, we have 2 times 12 equals 24. 2 and 12 are the factors, and 24 is the product. We can also get 24 by multiplying 3 times 8. So the factors are 3 and 8. And 6 times 4. Can you think of another way? I noticed that I could have also said 1 times 24. So 1 times 24 would be another way. So that gives us all of the factors of 24 then. We have 1, 2, 3, 4, 6, 8, 12, and 24. So remember, factors are numbers that we multiply together, and the result is called a product. So when we talk about divisibility, we're talking about, can I divide one number into another number without getting a remainder? If you remember way back when you were first learning, after you learned multiplication, then you learned division, we had these remainders. So for example, if I do something like dividing 3 into 10, and hold on, let me get my mouse back over to here. If I try to divide 3 into 10, why are we not working? Okay, something's not working right. So if I want to try to divide, this is not going to be pretty because my pen isn't working, but divide 3 into 10. Remember, it goes in 3 times. And then when we multiply 3 times 3, we get 9. That means we have a remainder of 1. So we have 3 remainder 1. So in order for one number to be divisible by another number, it has to be true that when we divide that first number by the second number, we get a remainder of 0. So if one number is divisible by another, we say that that second number b is a divisor of a, and we also say that b divides a, and we write this in shorthand like this, b with this vertical bar and then a. So this means 12 divides 24, which is true because we know that 24 divided by 12 is 2. We can also talk about rules for divisibility. Like, how do I know that a number divides another number? Well, if it's one of those in that range of we learned in school, typically we learn to multiply numbers up to 12. So 1 through 12 by the numbers 1 through 12. But then if we start getting into the higher numbers, then it's a little bit harder to tell, right? So if I think about 15, I know that it's divisible by 3 because I know 3 times 5 is 15. But what about 1015? Is that divisible by 3? Is it divisible by 5? So we have some rules that we can use, and we have rules for most of the numbers from 1 to 9. Obviously, any number is divisible by 1. For 2, though, remember if you count by 2, you get 2, 4, 6, 8, 10, 12, 14, 16, 18, etc. And notice that the last digit of all of those ends in either a 0, 2, 4, 6, or 8. So any number that ends with an even digit is an even number. An even number is just another way of saying it's divisible by 2. For divisible by 3, I can look at, does my number, oops. for divisible by 3, I can look at, does the sum of the digits in my number, is that a number that's divisible by 3? So for example, here where we have 52,341, if I add up those digits, 5 plus 2 is 7, plus 3 is 10, plus 4 is 14, plus 1 is 15. So all of these digits add up to 15, and I know 15 is divisible by 3, and that means the entire number is divisible by 3. So if you're interested in proofs, we can, of course, prove that, but that's kind of beyond the scope of this class. But I'm sure if you're interested, you could find it on Google how to prove that that's true. For divisible by 4, all I have to do is look at the last 2 digits. So with 2, I had to look at the last digit. With 4, I look at the last 2 digits. So the number 3,947,136, the last 2 digits are 36. 36 is indeed divisible by 4 because it's 4 times 9. So that means this entire number is divisible by 4. 5 is an easy one, right? We know that if you count by 5, you have 5, 10, 15, 20, etc. And if you look at all those numbers, you'll notice that they all end with either a 0 or a 5. So any number that ends with a 0 or a 5 is going to be divisible by 5. Here's a couple of examples here. In the next slide, we have 6. And what we have to do to check if a number is divisible by 6 is to remember that 6 is 2 times 3. So any number that's divisible by both 2 and 3 is divisible by 6. So for this example here, I first am going to check, is it divisible by 2? Well, it ends with a 4, which is an even number. So that means it's divisible by 2. Now I'm going to add up the digits. 9 plus 5 plus 4 is 18. And 18 is divisible by 3. So that means this entire number is divisible by 6. To check 8, this one's a little bit, not harder, but it's a little more work to do because I have to check the last 3 digits, which may not be obvious, right? 832. So I might have to do a little bit of long division or just divide with a calculator, right? I could take 832, divide it by 8 with my calculator. And as long as I get a whole number and I don't have any decimal part in my answer, then I know that it's divisible. Divisible by 9 is very similar to divisible by 3. I'm going to add the sum of the digits, and this time I'm going to check, is that sum of digits divisible by 9? If it is, then the number is divisible by 9. So for our example, we have 5,346. We add up all the digits, 5 plus 3 plus 4 plus 6, and we get 18, which is divisible by 9. So 5,346 is divisible by 9. And then we have 10, which is another easy one. And you maybe remember that any number that multiplies by 10 ends up with a 0 on the end, which means that any number that ends in a 0 we could get by multiplying some other number by 10. So that number has to be divisible by 10. So in this example, we have a 0 in the very last digit. That means 998,746,250 is divisible by 10. And then our last one that we're going to talk about is divisible by 12. And a number is divisible by 12, just like with 6, it had to be divisible by both 2 and 3. So for 12, it has to be divisible by both 3 and 4. And we have ways for other numbers, but these are the most commonly used ones that we're going to talk about when we're checking divisibility. So I recommend when you're doing homework asking you about divisible, just have a list of these rules nearby so that you can check. The next thing we're going to talk about is called prime factorization. Now, a number is a prime number. See if I can get this to work this way. Still doesn't want to work for me. Hold on one second now. Okay. Trying to get my pen to work, and it is not wanting to cooperate. Okay, I'll have to I'll have to debug this later. So I apologize for not being able to write neatly on the screens because my pen, for some reason, is not working today. A prime number is a natural number greater than 1. Very important here. Greater than 1. Okay. Which means, is 1 a prime number? No. 1 isn't greater than 1, so it can't be a prime number. So a prime number is a natural number that's greater than 1 and has only itself and 1 as factors. So an example would be 2. Okay, 2 is greater than 1, and the only factors of 2 are 2 and 1. 3 is also a prime. I cannot write without my pen. These are not pretty. But 3 only has factors of 3 and 1. Now for a composite number is a natural number greater than 1 that's divisible by a number other than itself and 1. So let's check. 1 isn't a prime number because it's not greater than 1. It's also not a composite number. So you want to make sure you understand 1 doesn't fall into other category, and that's okay. 1 isn't prime, it isn't composite, it's its own special number. Let's think about composite numbers then. The smallest one. So 1 is not prime or composite, and 2 is prime, and 3 is prime. So 4, let's see, 4 has factors of 1 and 2 and 4. So it's divisible by 1 in itself, but it's also divisible by 2. So it meets our definition of a composite number. And you might have noticed that it's that the only even number that's going to be prime is 2, right? 2 only has factors of 1 in itself, but every other even number is going to have 1 in itself, and at least the number 2 would also be a divisor. So 2 is going to be the only prime number. Now, does that mean that all of the odd numbers are prime? No, right? 3 is prime, and 5 is prime, and 7 is prime, but 9 has factors 1, 3, and 9. So 9 is a composite number. The next thing we're going to talk about is the fundamental theorem of arithmetic. It sounds scary because we use the theorem, but it's really not. It just tells us that for every composite number, we can write it as a product of prime numbers in a unique way, as long as we list the primes from smallest to biggest. And we use this theorem to help us with a lot of things involving fractions, like when we're adding fractions and we need to get a common denominator, or maybe after we've added or multiplied fractions and we want to simplify our fraction. And one of the ways that we do this is to find the prime factorization is by using what we call a factor tree. Okay, now it doesn't want to go. There we go. Okay. So let's look at an example. If I want the prime factorization of the number 700, I'm going to start with any two numbers that I know divide into 700. So we started here with 7 and 100, but we could have started with 2 and 350. Or we could have started with, let's see, 25 and 28. Okay, so it doesn't really matter. Start with any two that you know. In this case, we're starting with 7 times 100. And then I look at those two numbers. This one's a prime, so I'm done here. My goal is to get primes in all of these end positions here. So I've got a prime here. So now I look at 100 and I find a way to multiply to get that. And I might have said 10 times 10, or here we did 2 times 50. And now we've got a prime here. We're going to leave it alone. And we're going to factor 50. And one way to factor 50 is 2 times 25. That gives me a prime here at 2. And then 25, I can factor again, and I get 5 times 5. So you can see that the prime factorization is 7 times 2 times 2 times 5 times 5. Or if I want to reorder that, starting with the smallest prime and ending with the biggest prime, I would get 2 times 2 times 5 times 7, which we can also write as 2 squared times 5 squared times 7. right? Remember, 2 times 2, I can write like this. This means take 2, multiply it by itself twice, and this means take 5 and multiply it by itself twice. So as long as I write it this way with the smallest prime to the biggest prime, this is unique for this number, and it's the only number we can get by multiplying that way. And why is this helpful? One of the reasons it's helpful is that it helps me to find what we call a greatest common divisor. Again, really useful when I'm working with fractions. If I have two numbers and I'm looking for the biggest number that divides evenly into both of them without any remainder, what we call the greatest common divisor, I can do that by writing out the prime factorizations. I can take my two numbers, write out their prime factorizations, and then I know that in order for a number to divide into both of them, it would have to be made up of a list of factors that are in both of them. So once I've got those prime factorizations, I can just look at, for each prime number, any prime number that's in both of them, I'm going to take all of those and multiply them all together. Let's take a look at what that looks like. If I want the greatest common divisor of 216 and 234, I'm going to first write the prime factorizations. So you can see 216, here's one way of factoring it. So I've got 2 times 2 times 2 times 3 times 3 times 3. And 234 is 2 times 3 times 3 times 13. And you can see they have a 2 in common, and they have two 3's in common. So that means the greatest common divisor is going to be the number I get when I multiply 2 times 3 times 3, which happens to be 18. Another way of looking at this is if I write those prime factorizations, so instead of looking at the factor tree, I take all of those factors. And to get 216, we had to multiply 3 2's and 3 3's. And to get 234, we had to multiply a 2, 2 3's, and a 13. So what do they have in common? Well, this one has 3 2's, this one only has 1 2, so that means they have a 2 in common. And then this one has 3 3's, and this one only has 2 3's, so they have 2 3's in common. And then this one has a 13, but the other one doesn't. So what they had in common was 2 and then 2 3's, or 2 times 3 times 3, which we can also write as 2 times 3 squared, which is 2 times 9, or 18. So that's one way of getting the greatest common divisor. Sometimes you look at a couple numbers and you can just kind of figure it out. If I gave you smaller numbers like maybe 18 and 12, you might remember that they're both divisible by 6. But that's the biggest number that goes into both of them. So for that one, you might have even just kind of thought about what are the numbers that divide into 12 and what are the numbers that divide into 18 and what do they have in common. But with bigger numbers, this technique that we just looked at is really effective and works quite well. Now let's talk about the least common multiple. So this is the one that we're going to use when we're trying to add fractions and we need that common denominator. And while it's not absolutely imperative that we get the least common multiple, it makes our arithmetic simpler. So usually we do prefer to get the least common multiple when we're adding fractions. And it's kind of, you can almost think of like the reverse of the greatest common divisor or greatest common factor. So for the least common multiple, now I want the smallest number that both of my numbers divide into evenly. So there's a couple ways of doing this. We're going to look at one in detail, and then I'll tell you another way that I do for a shortcut with smaller numbers. So with big numbers, I really like this method that's in the PowerPoint. Just like we did for our previous process, we're going to start with the prime factorization of each number. But now notice that in order for a number, in fact, let's look back at our example here. In order for a number to be a multiple of 216, it has to have factors that include 2 3 times and 3 3 times because that's what's in here. And in order for a number to be a multiple of 234, it's got to have a 2, 2 3s, and a 13 as factors. So when we were finding the greatest common divisor, we took the smallest of each, right? We took 1, 2, and 2 3s because that's what they had in common. Now I want everything that's in either one of them. So for the least common multiple here, I'm going to need 3 of these 2s, 3 of the 3s, and a 13. And I'm going to multiply all of those together. And that way, both 216 and 234 will divide into the number. And so that's what this process is telling us to do. Let's walk through it with some new numbers here. So we have 144, and if we made that factor tree, we would find that we have to multiply 2 times itself 4 times, and 3 times itself twice, multiply those two together, and we get 144. And a factor tree for 300, we would have got 2 times itself twice, 3 once, and then 5 times itself twice. So for that least common multiple, I'm looking at the biggest of each. So here, if I take 2 to the 4th, notice that that takes care of the 2 squared because that's in here. There's already 2 of them. If I have 4, I definitely have 2. And this 3 is taken care of here because I have a 3 squared. And then I need the 5 squared. So I'm just going to multiply 16 times 9 times 25, which gives me 3,600. So the least common multiple of 300 and 144 is 3,600. Now, if I'm working with smaller numbers, again, let's see if I can write some really messy things here, but say, let's just talk about 12 and 8. I want the least common multiple of 12 and 8. So another way to do this is to take the bigger number, which is 12, and then start thinking about what are multiples of 12. So the first multiple is just 12 times 1, which is 12. And then I say, well, does 8 go into 12? Nope. So this isn't the least common multiple. And then I say, well, let's double it. 12 times 2 is 24. Wow, that's messy. Does 8 go into 24? It does. 8 times 3 is 24. So that means 24 is the least common multiple. So you see, I think for smaller numbers, this is a little bit easier way to go than writing out those factor trees and using this long technique. And what I did is I just take the bigger number, list its multiples, and as I list them, I'm just checking to see if the smaller number divides in. As soon as I find the one that the smaller number divides into, that's my least common multiple. And this will work with the big numbers too. It's just writing out multiples of 300 isn't that hard. But if I had something like 352, that's kind of a lot of work to list those multiples. And it's also a lot of work to try to divide the other number into it. So I recommend this for smaller numbers. All right, let's look at an application problem. So we have a movie theater and they have 2 movies running. One of their movies runs for 80 minutes and the other movie runs for 120 minutes. And both of them start at 4 p.m. And what we want to know is when will they begin again at the same time? So if they start at 4, you can see that, let's see, in 80 minutes, it would be 5:20 p.m. So this one would be getting ready to go again, but this one would still be running in its first run. So really all we have to do is find the least common multiple of 80 and 120, and that will tell us when they're going to run again. Oh, and guess what? That's related. I didn't even do that on purpose, but it's related to the one we did in that previous slide, right? We had 12 and 8, okay? And we said 24 was the least common multiple. Well, 8 is just 10 times 8, and 80 is 10 times 8, and 120 is 10 times 12. So the least common multiple is going to be 240. And if that was a little too much math for you, let's just take a look on the next screen. Okay, so I can also write those prime factorizations. So to get 80, I have to multiply 2 times itself 4 times, and then times 5. 120 is 2 times itself 3 times, times 3 times 5. So again, I'm taking the biggest of each, so I need to take 2 to the 4th, and then I need a 3, and then I need a 5. So 2 to the 4th times 3 times 5, which is 240. So back to my problem, that means that after 240 minutes, the movies will start again at the same time. So now I have to think about 240 minutes. Well, if there's 60 minutes in an hour, 240 divided by 60 would give me 4 hours. So that means after 4 hours have passed, the movies will begin again. 4 hours after 4 p.m. would be 8 p.m. And there's the answer to my question. That's the highlights of what we're looking at in this section. The other thing that I wanted to, oh, you've joined me. Is it Shaylin?
Yeah, it's Shaylin. I've been here since the start. I'm just listening.
Oh, okay.
Have
See,
my AirPods in.
when I first started, there was nobody there, so I thought, well, I need to make a recording. Do you
Oh
have,
yeah.
I'm so sorry. In the way my screen is working, it wasn't show, it wouldn't show me both. I need to do a little debugging of my setup here.
Yeah, a lot of my
Anyways,
instructors had that same issue as well. And then when they have it on the pin, they can't scroll to the next page. I've noticed that a few times in a few of the lectures.
yeah, see, I have a new system and I thought I used this system last week and it worked, but I must have been on my old system last week. Anyway, so what questions do you want me to answer? The other thing that I was going to do is I looked at this module from last week and I looked at the problems that were missed the most often. So I was going to do some similar examples, but do you have any questions for me?
No, I'm just here for this, just the extra review. I watched Dr. May's lecture as well, so just a bit of extra review. I have my AirPod in and I'm just listening.
Okay, so then I'm going to pull up my next PowerPoint, which is going to be a few problems that, as I said, this module last semester, my students did really well on, but there were 3 problems that I identified that looked like were a little more challenging.
The
So I'm
word
going to do those. Say
is it
again.
is it the word problems?
Um, Now one of them is a word problem, and
Okay.
if there's another problem that you want me to do, I'm happy to do, whatever. You're here, so I'll do whatever you want to do.
I don't have any
Um,
specific. I'm just here for just the extra review.
okay. So then, okay, so yeah, this was a word problem, obviously. Well, kind of a word problem. And I think these sometimes throw people, these ones that are like, decide whether it makes sense or not, right? And in these, since these are multiple choice, a good approach to doing a question like this is first decide, does it make sense or does it not make sense? And then try to figure out for yourself why or why not, and then look for that choice. So let's see, this one says I need to separate 70 boys and 175 girls into all male or all female teams, and I want the same number of people on each team.
Is your
So,
screen's not your screen's
oh, I'm so sorry.
okay?
Thank you. I'm so glad you're there. My other ones did show, right?
Yes, everything else did show.
Okay. Oh, you know what? It was my mistake. I got so excited someone was there, I forgot to share my screen. Okay, let's see. Here we go. All right. Now you can see it, and let me put it back into, and now you're seeing it as a slide, right?
Yes, I can see it.
Okay,
Oh,
beautiful.
nope.
Oh, I hit the wrong. See, I do that sometimes. I go to try to annotate and the button is right by the stop share and I miss it.
There it goes.
Yes. Okay. So now there I got the button without stopping the sharing. Okay. All righty. So we have, here we go. So does this make sense or not? I need to separate 70 boys and 175 girls, and I want all male or all female teams, and I want the same number of people on each team. So it's not asking me to do it. It's just saying, does it make sense that I would find the least common multiple? of 70 and 175. So if I found the least common multiple, and what I think confuses people is they hear least and they think small. But if you think about the least common multiple is always at least bigger than one of the numbers, right? It could be like if I had the numbers 8 and 4, the least common multiple would be 8. Okay, but if I have numbers where one of them doesn't divide into the other, then my least common multiple is always bigger than the numbers that I'm finding the least common multiple of. So if I were to find the least common multiple, it would be bigger than 70 and it would be bigger than 175, and I wouldn't even have enough kids to put on any of my teams. So that doesn't really make sense to me. What does make sense is that I would want the greatest common factor because I'm dividing these up. And so if I found the greatest common factor of 70 and the greatest that it had in common with 175, well, now I can divide it into both of them and end up with even numbers of teams. So don't get fooled by that greatest common factor in the least common multiple. The greatest common factor is going to be a smaller number than at least one of the numbers, and the least common multiple is going to be bigger than at least one of them. All right, okay, here's a big one. Here's where I really wish my pen were working because I am not good trying to draw these with the mouse. Okay, so to find the least common multiple, I'm going to make a little factor tree here. And for a number like this one, let's see. Well, normally I would start with 2, but I noticed that 4 is actually going to go in because 4 goes into 44, those last 2 digits. And for one like this, you can do the long division. You can also just do a quick, calculator. I think 4 is going to work. So I can divide 4 into 5,544. And let's say I get 1,386. Okay. And let's see, 4 is not going to go into that. What about 3? Let's see. 1 plus 3 is 4, plus 8 is 12. But yes, 3 is going to divide in. So I'm going to do 3 next. So 3. Oh my gosh, I'm horrible with this. 1,386 divided by 3 is 462. And let's see, that's also divisible by 3. Divide by 3 again. And I get 154, which is not divisible by 3 because 1 plus 5 plus 4 is 10, but it's divisible by 2. And if I divide 154 by 2, I get 77. And I know that 77 is 7 times 11. And I'm almost done because 11's prime, 7, 2, 3, 3, but 4 isn't prime, so I got to come back up here and make that 2 times 2. Oh, okay. So let's see if I can write that over here. I've got 1, 2, 3 2s, so that's 2 cubed. Ooh, it's ugly. Okay, and then I've got 1, 2, 3s, so times 3 squared. And then I've got a 7 and an 11. Okay, and then let's see, I'm going to erase this. So 2 cubed times 3 squared times 7 times 11 gives me 5,544. And I notice that this is going to be divisible by 11. This is going to be 11 times 300. And then 300 is 3 times 100. And 100 is 2, 2 times 50. And 50 is 2 times 25. And 25 is 5 times 5. All right, so that means 3,300 is going to be, let's see, I need two twos, so 2 squared.
Is there, I have a quick question. For the
Yeah.
2 times 25, you just, was there a reason you chose 2 and 2 and 25, or can we have done 10 and 5?
Yep, no reason. You can choose whatever you want.
Okay.
Yeah, the only thing that you have to do is you got to keep going as long as you don't have a prime.
Hmm.
So if I would have done 5 and 10, then I would have had to factor 10 into 2 times 5.
Okay.
Yeah. And then it would just be in a different order. But yep, doesn't matter which way you do it. So 2 squared and then 3 and then 5 squared. Oh my gosh, that's so sorry. I am really, let me see if I can. Oops, wrong one. Try that again. 5. Ugh. It's like trying to do some people can use like an Etch-a-Sketch and make really beautiful drawings, but I'm not one. Okay, 2 squared times 3 times 5 squared times 11. Okay, so for my least common multiple, I'm going to start with 2. And again, it has to be the bigger of them. So 3 is the bigger one. So I'm going to take 2 cubed. And then for the 3's, I've got a 3 squared and a 3. So I've got to take the 3 squared. And then I need a 5 squared. And I need a 7. And I need an 11. And then if I multiply all those out, so 2 cubed, that's 8 times 3 cubed is, sorry, 3 squared is 9 times 2 squared is 25 times 7 times 11. I get 1,925. And then I could just check. Let's see, if I divide that by 5,544, it goes in, whoops. No, I did something wrong here. Hold on. Glad I checked. Let's see, 2 cubed times 3 squared times 25 times, whoops, 7 times 11. Oh, yes. I'm glad I checked. That is not right. I wrote something down wrong. Oh, that was obviously wrong because it wasn't even big enough. I was just not really paying attention. Okay, so now I get 138,600. Let's check that. 138,600. If I divide it by 5,544, I get 25. That sounds better. And if I divide 138,600 by 3,300, I get 42. Yes. All right, we did it right. Beautiful. Any other questions about that one?
No.
Okay. And then the other one that was a common struggle. And I think a couple of these came actually from the quiz. Let me see, hold on. I cleared it. Okay.
Yeah, I got that one wrong too because I kept getting 155 point, I believe, 8. And it kept telling me no both times. And so, yes, this one was one that I got wrong.
Okay. So we basically have 155 pounds plus 13 out. You can think of it as pounds plus ounces, right? And then if I convert my ounces to pounds, I need to multiply by that unit multiplier that has ounces in the denominator and pounds in the numerator. So how many ounces are there in a pound? So a pound is 16 ounces.
Every
So,
time I keep trying to unmute my phone,
oh,
it
that's
won't
okay.
let
That's
me.
okay. Yeah. Yeah, no worries.
1 pound is 16 ounces.
Yeah. So what I have to do is I have to do 155 plus 13 over 16. And I'm going to use a calculator for that. Let's see, what is 13 divided by 16? Whoops. 13 divided by 16 is 0.8125. So 150, ugh, try that again. 155. Oh my gosh. I am so not good at this. 8125. 155.8125. And I believe this problem said don't round it. So I would leave it exactly like that.
I think it did. I think it did say round because oh
Okay, well, if it
maybe
wanted
not.
me to round, then I just need to know which place it wants me to round it to. Um, are you in my class?
No.
Oh, okay. I was going to say I could check, but every once in a while, so another kind of feature of Canvas is that we have to give it like all the possible answers. So, for example, it doesn't know the difference, or it knows the difference. So it 155.8125 space LBS is a different answer than 155.8125 no space LBS. So we have to remember to give it both answers, and sometimes we forget one of those. So there's always that possibility. If you're doing a problem and you think you're doing everything right, I would send it to your professor and say, hey, is this, because there, we still find a few mistakes. It's not a perfect system. Unless you know which problem it is, we can look at it. Like if you have it.
I know for sure it was this one. I don't have
Oh,
my lap
okay.
with me, but I don't know. I can't remember if it said round, but I think I kept rounding it to the hundreds, and so then I would get um the 155.8.
Mm-hmm. Hmm. Yeah. Well, take a look at that, and if you think you're doing it right, send it to your professor. Because
Okay.
I have seen a couple of these this semester, and we just keep adding them in. Oops, we need to fix that one.
Okay.
But it's a really easy thing if you did actually get it right, but it's just a problem with Canvas not recognize it as correct. They can fix that for you.
Okay. Thank you.
Mhm. All right. Any other problems you wanted to look at?
Let me see if I can try to log into my app.
Yeah.
Okay, so the 96 kilograms equals how many pounds? And then it says round to the tenths.
Oh, okay. So that's actually a little bit different because you're converting 96 kilograms. Okay. Converting 96 kilograms to pounds.
Using the conversion factor of 1 kilogram. equals 2.2 pounds.
Okay, so 1 kilogram equals 2.2 pounds.
And then it says round to the tenths.
Tenths. Okay, so let's do that one. So then the unit multiplier that we want to convert to pounds. So that means I'm going to put pounds in the numerator of my conversion factor. So I want 2.2 pounds numerator and 1 kilogram. Is that how you did it?
Well, I did the 96 times 2.2.
Okay. So we get 96 times 2.2 and we get 211.2.
Yes.
Okay. So it might be
And
I'm
then it
pretty
says
sure.
round to the tenths. So would the 0.2 drop?
No.
Oh,
So
because there's nothing in the hundreds.
it's already rounded. So there's nothing to round. So we don't have anything to the right of this position. So we already have the accuracy that we wanted, 211.2. So that's your answer.
Oh, okay. I dropped the 0.2.
Oh, okay. Yes.
Okay.
So whatever place you're rounding to, that's the last digit that you're going to have. And you're going to have at least a digit here. Okay. So if you had some number to the right of it, then you would have to decide whether to change it or not. But if you don't have anything there, then you're done.
Days. Okay. That's why I,
That's why we figured one out. Good.
yes, thank you.
Yeah.
And it was
Fantastic.
fun.
Any other ones?
Nope, it was just that one and the 155 pounds, 13 ounces.
Okay.
So that was all.
All right. So things are going well for you in the class then?
I think so.
Good.
I've been trying
Good,
to
good.
many as I can, or just watching them or putting it in my ear while I'm cleaning or something. So that's been.
Yeah, that's smart. Yeah, good idea. Yep. Good way to learn things. Just immerse yourself in it.
Mhm. Well, thank
All
you
right.
so much.
Say that again.
I said thank you so much for your time.
Oh, oh yeah, absolutely. Yes, you're welcome. I'll be
Okay.
here same time next week.
Okay, I'll join. Talk to you soon.
All right.
Bye bye.
Bye.